All right. So, what do you guys want to discuss today? I wanted to discuss those directional derivatives, and then I wanted to discuss wedge products and differential two forms. But do you have any specific question in your mind that you want to ask? If so, please
I had
ask.
a question.
Yeah. Okay.
Assignment 3, last question to how do we do it?
Oh, so what you do in assignment three's last question is that first of all you have to integrate by parts n times to get rid of that x to the power n. Or was it there was some x to the power m times exponential of a times x to the power n, right? If I'm not
Uh,
wrong,
yeah.
that was the. So first of all, you need to integrate by parts, uh, and when you do that integration by parts, m times that x goes away. Hmm. And then finally, when you encounter with the exponential operator or the exponential function, you write in terms of a series summation. I think most of you um, try to implement the incomplete gamma function, but the very definition of incomplete gamma function is defined through a definite integral, but that was an indefinite integral. Hmm. And you also have to use the conditions in the question. You have to do some sort of manipulation that this m plus 1 divided by n was some natural number, right? Like 0, 1, 2, 3, and so on.
Hmm.
So you need to incorporate that in your problem as well. Do you want me to post an explicit solution to that
Oh,
problem?
please, yes.
Okay,
That would help.
okay, okay. I'll do that. Okay, Nian is here. Okay. Anything else? Any other questions that you have in your mind?
I have one more.
Yes, please.
Go on.
Okay. Who wants to speak
If
first?
okay, so please, like my concern is about the mark distribution, the 5% reserved for class attendance. It's like I
Yeah.
missed almost all your classes, and I'm quite
No.
worried about my 5%.
No. 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 The class attendance is just coming from your MCQs that you see in VUX. Consultation classes are not mandatory, so there is no marks for consultation. I thought I
Okay, sir. Thanks, sir.
discussed it in the first meeting. Yeah. I mean, yeah, it's called class attendance, but since we are doing an online semester and consultation hours are not mandatory, all of those marks will come from your MCQs or so-called pop quizzes. If you have attempted all the pop quizzes that appeared in BUX, you are fine, regardless of whether it's right or wrong. So don't worry about that attendance marks. Okay, so I think Ishwar wanted to ask another question. Okay, you can ask.
It's just one small question. To use the hospital's rule, one of the things that's necessary is the function needs to be differentiable, right?
Mm-hmm. Yeah.
What does that mean? Isn't most of them differentiable? Like, how do I check for that?
So if you want to do it in a mathematician's way,
Mm-hmm.
then what you need to do is that first you have to check for continuity. Okay.
Hmm.
First, you check the conditions of the continuity, whether that function is defined on that point. Then you take the limiting values, and the limiting value, if the limiting value is equal to that value of f of a, let's say to some point a, then you say, oh, this is continuous, fine. But
Hmm.
how do you know this is differentiable? Okay, so you need to impose another restriction. You calculate the limits from both the left hand side and the right hand side. And if you see that, okay, the left hand limit and the right hand limit, they're the same thing as well. So that tells you that that function is differentiable on that point. And then you
Um,
can go into L'Hopital's rule. People use it blindly because most of the functions we deal with are pretty nice, but there might be functions, for example, piecewise functions. Those piecewise functions are not that nice. So you can use L'Hopital's rule, but yeah, you need to take care of that thing, that whether it's actually differentiable or not, because there might be functions which are not differentiable at all. So
all
there
right.
is sort of confusion. Yeah.
Thank you, sir.
Okay. Okay, anything else? Uh, if not, then I think everyone is having trouble with forms. I discussed some how you deal with differential one forms in the last discussion, and it's in BUX. If you want to check that out, feel free to do so. So today I want to uh, give a brief review of this directional derivative, and then I want to move to wedge products. So let's start. So the first thing that we want to discuss is something called a directional derivative. And this is the most general kind of derivative, at least from my perspective. I think this is the most general kind of derivative that you can have. Why? Well, let's see. So let's consider a function which is a function of x and y only, so that we can plot it in our 3D space as a surface. So let's say our function is something f of xy, and let's say this is our surface, okay, where I'm denoting z is equals to f of xy. So
Sorry, you're not
when you
visible your screen.
yeah, sorry, oh yeah, I forgot to share the screen. Sorry, I didn't sleep last night, so I'm feeling a bit dizzy. And I keep forgetting things, so in case I make any kind of mistake, you should point that out, because I think you have already seen the lectures and all that. So now you can see, right?
Yes, sir.
Okay. So what I like to think of directional derivatives is that, okay, you have some functions like this, and now what you want to do is that you want to know how this function changes. Well, if it's a one-dimensional case, it's pretty straightforward. There is only one variable to consider, but when it's more than one variable, you can go into different directions, right? Because consider the one-dimensional case. By one dimension, I mean there is only one variable. So something like this. So what you can do, you can either go in the positive x direction or in the negative x direction, right? But when you incorporate another variable, you have some more degrees of freedom to move around on that surface. A puppy, let's say, he wants to play. How do you draw a puppy? Like this. Yeah, it looks like a cat, but whatever. So when you incorporate two variables, you can go into different directions. And the function might change in different ways depending on in which way you are moving, right? So that is one motivation behind this directional derivative. And in mathematical terms, what we do is that we say, let's say I have a function. I have a function f of x, x1, let's say x2, x3, dot, 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 x of n. I'm doing this for the most general case possible. That means there are n variables. Now, obviously, you cannot draw this thing because it would require an n plus one dimensional space. So it's good to sometimes adopt this abstract notations. It will make your logical understanding a bit more solid. So that's why I'm going with the n variable case. So let's say I have this function, and what I want to do right now is that I want to find solution to a problem that says that, okay, now let's say, so this is the statement of the problem. Let's say I move a1 units in the x1 direction, a2 units in x2 direction, and so on. an units in the xn direction, right? So how will my function change if this is my condition for moving? So what we do, we define the directional derivative in the following way, that if I have this sort of a problem, the directional derivative will be defined as the following. It will be all this x's encoded into a vector like this, even though we sometimes omit this arrow sign. Then there will be some scalars, some scalar t, and then we take into account the displacements or the deviations that comes from moving into different directions. That is this a1, a2, a3, and so on. And all of this can be encoded in another vector, let's say a, that has some components like this. And we started from where? We started from some initial point. Let's say that initial point is this x over here, because x plus ta is not the same as x, because there is some additional parts over here. So we need to subtract it. And now what we need to do? We need to divide it with something, and finally we want to take the limit to be 0, right? I mean, that's how we ordinarily define our derivatives, through the definition of a limit. So notice that there's this parameter t. So this t controls how much you move, because t gets multiplied with this all these a's, right? So you divide it by t and you take the limit, t goes to 0. This is the definition of your directional derivative. Up to this point, is everyone okay? Is everyone clear on this whole thing? Or do you have a confusion that you want to discuss? If so, you can speak up. If you don't understand, you should let me know. Do you understand up to this point, everyone?
Yes, sir.
Okay, good. So this is the directional derivative, that's fine. But this definition itself, even though it gives us the foundation for the directional derivative, doesn't tell us much, because we all know that if my function is a bit complicated, then evaluating this quantity over here, let's call this equation 1, let's say, this evaluating this quantity would be a hassle. So we need to look for another way, whether we can do it, more easily and all that stuff. So what we do right now is that, since this definition incorporates the tools from the limits and all that, what we do is that we write this as the following: d dt of f of x vector t, and then there is this a, like this. And now what we can do, we can think of this function, which was initially a function of x only. We can now think of this as a function of what? X, t, and a, right? And a's are constant. So what we do essentially is that we take it as a function of x and t. And now what we can do, we can use the chain rule. If we use the chain rule, then this whole thing becomes pretty easy. Does anyone remember how to use the chain rule? Or can anyone tell me what should I write in the next line?
So you write
So, okay, let me make it a little bit easier for you. That is,
So,
instead of these vectors, yeah, Albert.
so I was going to give the answer, but if
Okay. So instead of writing these vectors, you can write it as a component, right? So if you write it as a component, it will look something like this. Now try to use the chain rule. If you use the chain rule, well, it's simply the partial derivative of f with respect to x1 at first. This is the first term, and there will be a derivative of x1 with respect to t, right? Similarly, will be x2, dx2, dt, and so on. Like this. And you can even write it as a compact notation using the summation symbol. Keep some index I that varies from 1 to n, because we have variable ranging from some index 1 to n. That's why 1 to n. Then you write df dxi dt, like this. But now, is there any way to simplify this expression? The answer is yes. Well, if you look at this expression over here, I'm denoting with a red line, is that it's saying that this is x1 plus ta1, right? But what we did over here is that we are taking derivatives of x1 with respect to t. Now that quite doesn't make any sense. Do you know why? Because this x1 plus ta1 is the new variable that is replacing the previous x1. That is, previously, when you didn't move on the surface, your function was a variable of what? Like, it has x1, x2, x3, dot 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 xn. But now it's replaced with x1 plus ta1. So if you wrote it as some x1 prime, the chain rule should look like this. Because think of it like this: x1 is not dependent on t, right? So if that's the case, then all these terms are zero identically. All of this is zero. Doesn't make any sense. Do you get my point? So that's why you need to consider this x1 plus ta1 as the new variable. If you want to denote it as x1 prime, you can do that. So these variables, these new variables, they will be denoted with prime, and you need to take the derivative of these new variables with respect to t. So if you do that and replace these things with primes, then consider this variable over here, that is x1 prime, which is denoted as x1 plus at, sorry, a1t, and you want to compute the derivative of x1 prime with respect to t. This is what? This is just a1, right? Similarly, if you have this quantity, it will be equal to x2, and so on. Dx prime of n dt would be a of n. So these quantities will reduce down to a of I, because this is reducing to a1, this is reducing to a2, the other one would be a3, a4, a5, dot 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 dot, a of n. So again, xi prime, there will be this ai, right? Is this okay with everybody?
Makes
Do you understand?
sense.
Yes, sir.
Yeah. So that's why I didn't use the prime at first, because I wanted to show you, okay, if you don't use prime, what happens? Okay. So now this is a good expression because we can use it easily. That means if you have a function, a multivariable function, and you want to uh, take a directional derivatives along certain direction, those direction will be encoded by some numbers, and you can use those numbers to construct a vector, right? Because you are going in some direction, so you can obviously use a vector to denote the direction. And now what this expression, let's see equation 2, it tells you that you have that function, fine, take the partial derivatives and multiply with the components of the of that vector that you are going to move along with, So let me show you an example. Maybe that will clear things up. Let me see. Is there any good example that I can show you? Okay, I think I have one. So let's say this is an example. Let's say our function is something like this: x, y, z, x square, y cube. Again, this is an example from book, so if you want to look it up, I think it's on page 64. আচ্ছা, I have to mute myself. আজান দিবে, so তোমাদের কান ফেটে যেতে পারে. Oh god. Let me mute myself for a minute. Acha, I think someone said something. Wait. Is it from Fortney's book? Yeah. Is it from Fortney's book? Wait, what? It isn't there? আমারটাই তো আছে.
আমারটা তো নাই দেখো আচ্ছা
Maybe the page number is different, maybe. I don't know. আমারটাই তো আছে. Like I have this one. Yeah. আমি এক্সারসাইজের গুলো করাচ্ছি না ইচ্ছা করে, কারণ ওগুলো তো অনেকগুলো তোমাদের হোমওয়ার্কে দিছি, সো ওটা করাবো না. Okay, so what I've been writing by the time I was silent was that you have a function like this, x square y cube z, and you want to move along a direction that is encoded by a vector given by 1, 2, 3, where 1 tells you that the how many units you should move along the x direction. 2 tells you how many units you should move along the y direction, and 3 tells you how many units you need to move along the z direction. Okay, and then we can use equation 2. I explicitly wrote it out. Now it's just a matter of taking partial derivative. So if you take the partial derivative, this is just what, 2x y cubed z. By the way, is there anyone who is not comfortable with partial derivatives? If so, you should let me know. Partial derivative means that when you are differentiating with respect to x, you treat every other thing, whether it's a variable or not, as a constant. Okay, you are only considering the x to be a variable. So that's why this x square y cube z, when I differentiate this guy with respect to x, I treat y cube and z as a constant, and I only differentiate with respect to x, and that gives me 2x multiplied with y cube and z. And v1 is this 1, that is the number of units you need to move along x direction. So you need to multiply with this guy with 1. Similarly, the second and third expression would be something like this. Let's say 3x square y square z multiplied with what, 2. And finally you have x square y cube multiplied with 3. So the result is x y square z plus 6x square y square z plus 3x square y cube. And if anyone tells you, okay, you found the derivative, that's fine, but I want you to evaluate this derivative at a certain point. So this is the directional derivative, that's fine. And if I say find the derivative, by derivative I mean the value of the derivative at point, let's say 1 0 1, and let's call that point P. So after you calculate this derivative, just like single variable calculus, what you need to do after your calculation, you just need to evaluate it at point P. So just plug in the numbers for x, y, and z. So this will be df at point P is just 2 times 1 times 0 times 1 plus 6 times 1 times 0 times 1 square, 0 square, whatever, doesn't matter. 1 plus 3 times 1 times 0. Oh, this is 0. Whatever. So do you get the point on how to calculate these things? Is it okay? Everyone is comfortable with this?
Yes, sir.
Okay. And now what we want to do is that we want to look at some special cases, because note that this is a very general case. The vector you are taking can be any vector, right? So look at this figure again. And let's say now instead of having any kind of general vector, you want to incorporate the unit vectors. The unit vector means this x hat, y hat, and z hat. Okay. What happens when you do these kind of things? Well, you already know the unit vectors have a value of what? A unit magnitude. And all the components on the vector that is telling you to, okay, move along this direction, all those components will have a value of what? 1, right? So this is a special case that we want to see right now. Of the directional derivative, where the vector v, let's say, or a, whatever you want to call it, will only compose of the unit vectors. That means 1 1 and 1. So if you have any sort of a function I'm giving it from 1 to 3 since we are dealing with a three-dimensional vector and a function of three variables. This will be xi times 1 only. Why? Because all the components are 1. I can obviously write it like this. Let's say vi, and then I can expand the summation x times v1 df x2 v2 df x3 v3, and all these components are 1, right? So if you plug in the values, what you are getting is something like this. This is one type of a special case. Sorry, I should write it as y and z. Sorry about that. Y, z. This is one sort of a special case. And there is another special case. In fact, it's almost the same as this one, the special case number 1, let's say. If you recall that the vectors are written like this, an n-dimensional vector, or for our discussion to make things simpler, we can have a three-dimensional vector. I can write the vectors with their components and their basis vectors, right? And now you already know that these basis vectors, they're equivalent to some differential operators. Is everyone okay with this?
Yes, sir.
Okay. So can you think of a way to extract out, I mean, by using the ideas of the differential forms or one forms, can you think of a way to extract out these components out of these vectors? Do you think there is any way using the idea of differential forms? Okay, so let me boil it down. So my goal is to extract out these components. I want to have this only. And what we have learned from differential one forms is that if I have a cotangent basis and you have this tangent basis, they give you a Kronecker delta, right? When I and j are equal, this is equals to 1, and when I and j are not equal, that gives you a 0. So for our case, a three-dimensional vector, let's write it like this first, 2e2. I'm ignoring all these hats because I mean, it's really painful to write these hats and arrows and all that. Okay, so next, in the next line, what I can do, I can write it like this: x1 v2 del x2 v3 del x3. Now let's say I want v1. How do I extract out v1? Right, simple. Take dx1. We know that differential forms act on vectors, so using that idea, I can write it like this: I want to use dx1 operator or differential form on this whole vector, this whole guy. Okay, and these are scalars, v1 v2 v3, they're scalars or numbers, so eventually by the property of the differential forms, they will, you know, escape its mouth or teeth, whatever you want to say it, and these differential forms will eat out these differential operators on the tangent space, or so to say the unit vectors on the tangent space. So it will be dx1 del x1 v2 dx1 del x2 v3 dx1 del x3, and all of this is 0. Just this guy gives you a 1 over here, so that gives you v1, right? So you can write v1 as dx1 v. So this is similar to a dot product thing. if you recall that from high school mathematics, that if you have a vector like this, 2x hat plus 3y hat, you could always extract out these two by dotting the x hat with the vector itself, right? Because x dot x is 1, but x dot y is 0. Why? Because they're perpendicular. Or so to say orthonormal, or so to say they belong in the dual space. But there is a lot going on here, because even though this x hat and this x hat, they look the same, they're not. If this one is on the tangent space, then this should be on the cotangent space. Or so to say, if this is a covariant vector, this is a contravariant vector. But we'll skip those technical difficulties for now. Okay. Okay, so is everyone lost, or I mean সবাই কি পাগল হয়ে গেছে এগুলা দেখার পরে? If you are lost, feel free to let me know. So my goal is to derive the total differential that you see from the idea of directional derivatives. That's my goal. So if we accept the, okay, whatever we did here, if we understood it correctly, then what I can do, I can go back to my definition of the directional derivative and substitute the new thing we just found. Let's say this is equation C. So we want to substitute 3 into 2. And if you do that, your directional derivative will now look something like this. df dx, yeah, given I from 1 to n I, and you had what, bi, and now you substitute. Instead of vi, you will have what, dxi, that is acting on a vector, right? So we are almost there. We are almost there, but all we have is this extra v that this differential form is acting upon. So there is another definition of this directional derivative. If you have seen the lectures, or if you have gone through the book, you know that you can write this directional derivative as the following as well. This vector is somehow acting on this function itself. And from there, you can say, oh, this is a test vector only. Like there are two ways. This is the rigorous way so far from my point of view, and there is the non-rigorous way. The non-rigorous way tells you, oh, this is a test vector, you know, because the choice of v is completely arbitrary. Let's say this is neon, and let's say this is Elon Musk. I don't know. No, Elon Musk is way too popular. Whom should I choose? I don't know. Captain Price, since I'm a big Call of Duty fan. So neon can go this way. Let's say this is denoted with some v. Ignore the 1. And Captain Price wants to go to this w direction. And if I have me, this is me, I want to go to this, I don't know, some z tilde direction. So this choice of v is completely arbitrary. So since it's completely arbitrary, you can think of it as a test function. We often call it test function in the context of differential equations, or you can call it a test vector. So you can just discard it. It will depend on the specific problem. That means, notice that this directional derivative itself relies on which direction you want to go. So you will always see there is a small v notation over here. So it tells you that, okay, this is your function, you want to move in the direction of v, and then this is your directional derivative, but this is what you should get. So you can call these v's as test vectors or test functions, whatever you want, and at the end of the calculation you can just discard it. So if you do that, then this directional derivative will now give you the total differential. I think it's called the total differential, right, Nian? Or absolute differential? I think it's called a
Total
total
different. Yeah.
yeah, total
Okay.
differential. 1 to n df dxi dxi. This is your total differential. So that's why I wanted to express that opinion that I consider the directional derivative to be the most general kind of derivative you can have. So you can get your total differential from it, because most of the time what we do, we say that this total differential is something intuitively that if you have a multivariable function, it encodes all the changes in your variables. That's how we intuitively define it. And the special case one that you saw earlier, where was it? Hmm. Where was it? Where was it? Yeah. This guy over here, this is also a similar expression to you. Do you know what it is? It's related with the gradient, but you have to dot it with the coordinate vectors. Like it's something like this. This is the gradient, and you have to move along the direction of what? Mm, okay, how do I write it?
I plus j plus k.
Yeah, I plus j plus কে লেখা যায়, but আর একটু কম্প্যাক্ট ওয়েতে কিভাবে লেখা যায়? It's more of a how do I express this thing? It's a very infinitesimal displacement vector. Okay, so this was one special case where d itself is 1 1 1. So you can get all sorts of this thing from your directional derivative and so on. Okay, no one is saying anything, so should I understand that everyone understood what I said all this time, or is everyone confused? If you're confused, you should let me know. And there is some pictures in the book, you can look into that as well, but I personally don't find the pictures to be really helpful, because it really doesn't make any sense when you go over 3 variables. Like, it's good to understand what goes around when you're dealing with 2 or 3 variables, but yeah, that's pretty much the equation. It just gives you the interpretation right away. So is everyone comfortable so far? Do you understand what I've been saying? Like, I don't know. I mean, I'm confused at this point whether you guys are understanding anything or not, so you should let me know.
I'll need some time to soak it in, but it makes sense.
Yeah. And at some point in life, nothing will make sense. You'll just get used to it. That's how science works, I guess. Because I personally, I don't know. I still don't understand thermodynamics. I just got used to it. That's it. Okay. Since we are done, and oh, one last thing. These are also one forms. This directional derivative, they're also one forms, because if you recall, I gave you this very BS shortcut explanation that how do you understand if something is a one form or two form. You just, see whether you have this dx's, how many dx you have. Since it has one, so this is a one form. Okay, but yeah, it has some rigorous definition, so please look into that. And since we are done, I think we can go to the last topic for today. We want to discuss something called the wedge product. So there is a lot of mumbo jumbo regarding all these volumes and all that. I think I covered some of that in my lectures. You can look into the book as well. I'm not going to go to the, why volumes are negative and all that. What does volume do when it has a negative sign and all that? Rather, I want to just focus on the computational part, on how you compute wedge products. So the wedge product is a new type of product that you see when you do differential forms or calculus on manifolds. So you have seen dot product and cross product, right? And recently you learned something called about something that is called inner product, that is a generalization of the dot product. So this wedge product can be thought of as a generalization of a cross product. Because cross product only works in 3 dimensions. That means when you have 3 variables, or so to say 3 coordinate axes and so on. 3D. In fact, 2 dimensional কিন্তু এটা কাজ করবে না. It won't even work in the 2 dimension as well. Cross product is a very special kind of product that only works in 2 dimensions. Okay. So let me give you a small motivation on why that is important. These cross products are actually antisymmetric. Why? Because if you have some cross product of 2 vectors, you know that A cross B is not the same as B cross A. Why? Because if you consider 2 vectors like this, A and B, you can build a parallelepiped, or is it parallelepiped? I don't know how to pronounce it properly. So you can have this parallelepiped or parallelepiped, whatever. And this cross product actually tells you something about its orientation. That if you have this A cross B, that means you use your right hand rule, and if you denote A cross B as C, then the vector C would point in the positive up direction or something, Z direction, positive Z, sorry. And if you consider B cross A, then it will point in the negative Z direction, right? So what does this have to do with anything? Well, in real life, when you consider the flow of something, let's say I have a tube like this tube. Obviously it has some cross section. This is some area, right? And what I can have fluids moving through this tube, and the fluids can move either way. It can go out, it can come in. So there are 2 ways, right? 2 orientations. So there is a thing called a flux, or so to say how much of the fluid is going through this cross section per unit time. I'm not going into the technical details, I'm just giving an intuitive idea. So if, let's say, we take the positive direction when the fluid goes out of the tube, so let's consider this orientation as positive and this one as negative. That means fluid going in, we're calling it as a negative flux. Fluid going out, that's a positive flux. And this flux will be written in terms of the fluid velocity and, if I'm not mistaken, the area vector. So when you take into consideration this orientations, you can actually tell about whether the fluid is moving in or fluid is going out. So that's one reason to keep notice of the signs of this orientation. That's what it physically means. I mean, you might do a calculation and you might see that, okay, my flux is negative. So what does that mean? That the net volume of the fluid is negative or something? No, it just means that the direction that you took as positive, the fluid is just going on the opposite direction. That's it. That's why those negative signs coming and all that. It has nothing to do with your calculation. It's just a physical interpretation. Now when you work with higher dimensional space or higher dimensional manifolds, you need to keep track of these things as well, otherwise things get really very messy. And if you okay, so do you guys know anything about Mobius Script? Have you heard anything called a Mobius Script? If you're not a physics major, I want you to answer. I think most of the physics and math major knows about it because it's pretty famous. But
Yeah,
what
I
about
do.
the other? Yeah, Nian Jan Beta Jani because you're the physics major. But what about the others? Do you guys know what is a Mobius strip?
Yes, sir.
I mean, if you have seen Avengers Infinity War, you should know about it. ওইখানে আছে এটা। ওরা হচ্ছে মোবিয়াস স্ট্রিপের উল্টা সাইডে গিয়ে তোমার ওই টাইম রিভার্স করে থ্যানোসরে পিটায়, ঠিক আছে? So Mobius strip is something that আঁকবো কেমনে? I don't know how to draw. Crap. Maybe how to draw this. Okay, so I'm not very good at drawing. Sorry. আমার ট্রাইও করা উচিত হয় নাই। So if you have a space like those Mobius strip or Klein bottle, and when you're dealing with your physical space where you have time itself, and when you go around that Mobius strip, the orientation of time, it flips a sign. So that's why these orientations are pretty important. So that's why we define something called a wedge product that keeps track of these signs. And these wedge products are also called antisymmetric products. Are also called antisymmetric products. And in fact, because of this wedge product, the Jacobian or the Jacobian, whatever you want to call it, pops out immediately. So what is a wedge product? Well, if you have a one form, let's say dx, you have another form dy, you can just wedge them like this in such a way that this dx dy and dy dx, they are not equal. In fact, they will be related with a minus sign, if I'm not mistaken, at this point. So this is the very definition of antisymmetry. What is antisymmetry? If you have two things, let's say two eggs, মুরগি ডিম আর হাঁসের ডিম, chicken eggs, goose eggs, or is it duck eggs, whatever. And if you interchange them, you will pick up a minus sign. And this minus sign is the guy that, he is accountable for the orientations. So what does this wedge product do? Well, first of all, if you have two one form, it gives you the ability to define a two form. So this dx dy, it's a differential two form. Most of the time we skip that differential word away because forms are differential. So yeah, so these are two forms. If you have something like this, dx dy dz, these are called three forms. If you have something like dx1 wedged with dx2 wedged with dx3 wedged with dxn, these are called n forms or differential n forms. And I have already told you that these differential forms are what? They are bases in the cotangent space, right? So what are these wedge products give us? This dx wedged with dy, dx wedged with dy, wedged with dz, and so on. Well, they are also bases. It's pretty hard to draw, but I can give you an idea of how this thing looks like. Let's say this dx dy, it's a two form, and all this dx and dy, they are what? They are bases on the cotangent space, right? So instead of thinking those basis vectors as a line, if you think for a second that the space that you live on and the bases you have are not lines, rather they are surface areas, then in that sense these wedge products will act as a basis as well. It's pretty hard to think of it, but it's pretty straightforward to show that they're basis vectors if you do some calculations. So they act as a basis. They are your friend to keep track of your orientations and all that. And there are more things that these wedge products can do, is that they define some sort of a volume form as well. And volume in this sense is a general term. Don't think of volume as a product of length times width times height. Rather, you can think of this dx dy as a volume 2 form. This dx wedged with dy dz as a volume 3 form. And this is a volume n form. So in some sense, it's giving you some idea about the orientation and some infinitesimal volume on your manifold. In 3D space, you can draw it. In higher dimensional space, you can't. Um, Up to this point, is everyone okay? Okay with this thing? It's a bit strange. It's a bit weird, but yeah.
So the volume 3 form is when you have 3 dimensions
Mm,
or 3.
well, you can also have 4 dimensions. I don't see any problem with that. Let's say dx dy dz wedged with dw, then it would be a 4 form. And the thing is, if you are working with a 4-dimensional space and you want to define a volume 3 form, I think that's absolutely fine. What you cannot do is that you cannot define a volume 5 form, because the other basis, it simply doesn't exist. Like if you have a 4-dimensional space denoted with x, y, z, w, you can always go for this dx wedged with, oh god, কি হচ্ছে এটা, dy dz, like this. You can always do that. For example, consider the 3-dimensional space, right? You can always have a surface area, তাই না? তুমি একটা কিউবও রাখতে পারো, আবার একটা সারফেসও তুমি রাখতে পারো, তাই, right?
Yes.
So I think of it like that. Yeah, you can have that. What you cannot do in a 3-dimensional space is that you cannot define an object that has a 4-dimensional volume. Okay, because the other axis simply doesn't exist, or the other degree of freedom simply doesn't exist. That would be unphysical. Okay. Anyone? Any questions so far?
Sir, also if you want to change in a differential 3 form, x is wedged with dy wedged with dx, dz.
DZ. Mm-hmm.
If you change it to dy wedged with dz wedged with dx, then that's equal. But
There's a minus sign because you know, if you interchange this y and z, what would happen in the coordinate axis? Let's say it like this. Okay, so this coordinate axis is a right-handed axis. Now what you are trying to say, okay, what if I change these two things? That means instead of writing dx dy wedged with dz, what if I write this dx wedged with dz wedged with dy? Well, that simply means this y and z, they got interchanged. And now this is not a right-handed system anymore. It's a left-handed system because you would pick up a minus sign. Simple.
sir, what if it was dz wedged with dx wedged with dy?
Same thing. Interchange.
Still have a minus sign.
For every interchange, you pick up a minus sign. But the interchanges, they have to be adjacent. This word, মানে পাশাপাশি চেঞ্জ করতে হবে আর কি. That's how the whole idea of anti-symmetry works. These interchanges, they have to be adjacent. Yeah, like you cannot interchange dz directly with dx. If you want to do that, what you need to do first, you need to pick this dz, interchange with dy so that it occupies the second plot. Okay, you pick up a minus sign. So let me show you. এই যে এটা আবার কাজ করতেছে না. Ubuntu 20.4 is full of bugs. ফালাই দিব এটা আমি. dx wedged with dy wedged with dz. Now what you want to do, you want to interchange dz with dx, right? That's what you want to do. So
Yes.
first you write dx wedged with, you interchange these two guys. Okay, so you write dz wedged with dy. But since there is this anti-symmetry property of differential forms, you pick up a minus sign, right? So there is a minus in front. Now what you want to do? You want to interchange dx wedged with dz. You want to interchange these two guys. So there is one minus and there is another minus. You have dz wedged with dx wedged with dy. And two of this minus will give you a plus sign. So dy. This is how you manipulate forms or wedge products and all that. I mean, this is how you deal with the anti-symmetry. And in fact, if you are interested, you can always look into how these wedge products are explicitly mentioned. I think it's defined by some sort of a tensor product. I don't exactly remember right now, but it's anti-symmetric product as well, and that thing is coordinate independent as well. Something like this. I don't know if this is 100% correct, but there is some sort of an anti-symmetry over here. But what I don't remember exactly right now is that whether these were y's and z's or whether it was something else. But there will be some sort of vectors. But if you don't know about tensor products, don't worry about it. So, Karo, questions? Is there anyone who has a question, who didn't understand anything, or who's thinking, what is all this nonsense and all that? It's fine. You can express your opinions freely. Everyone is silent. Or has everyone left? I don't know. Okay, so let's move on. So these are the type of manipulations that you'll get used to. I'm the assignment to DC, so if you have questions, let me know. And the last thing we want to do is that we want to see how this wedge product guys acts on vectors, because we said that the differential forms, they will act on vectors, right? They will eat up vectors and they should give us some sort of a number. That's the way we defined our differential forms. So how do this guys that comes with a wedge product acts on vectors? So how does this act on a vector? This is our question. Well, we have two differential forms. So if we had one differential form, we would need one vector to produce a number, right? Which was similar to a inner product, or so to say a dot product. And if you recall that your cross product, which is a special case of this wedge products, gave you a what? A determinant? Do you remember? So if you had something like this, you would calculate the modulus of it like this. Let's say in three-dimensional space. Some x, a y, a z, bx, by, bz, and this is what? A determinant, right? Even in three-dimensional space, if you had an object like this, you could calculate its volume. Let's say this is a vector, this is the v vector, and this is the c vector. You could always calculate the volume like this, a dot b cross c. Or its other cyclic permutations as the following: ax, ay, az, bx, by, bz, cx, cy, cz, right? So maybe this will also be featured in these wedge products when they act on the vectors. And the answer is yes, because at the end of the day, you are working with forms. Forms will eat up vectors and they need to produce a number. If you follow that ideology, then you can write this product. Let's say we have two vectors, v and w. It will act like this. And obviously our v has two components. It might have more components as well, and we'll get back to that in a few moments. But for now, let's just accept that v and w, both of them has two components like this. So this will act as the following. If you have dx wedged with dy, you will just have this dx acting upon this vector, then dx acting upon the w vector, then you will have dy acting upon v and dy acting upon w. So why am I doing that? Well, in short, wedge products are antisymmetric, determinant is antisymmetric, determinant has to do something with volumes, you already know. So this is the most sensible mapping that you can define. Obviously there is a way to do it, define it. I discussed it in the lecture, but my goal is here not to give you the whole rigorous thing, but to give you the idea of how you can compute all these stuffs. Okay, এটা কি বুঝতে পারছি সবাই নাকি? And this is just a determinant, that's it, nothing else, nothing fancy. There's nothing fancy about it.
Sorry, if we are asked to take the wedge product, then we'll just take the determinant of the Jacobian vectors.
Depend করে, it depends. Let's say I have some guys like this, dx wedged with dx2, dx1 wedged with dx2. I ask you to take a wedge product, this with some, let's say, x squared dx5. Then determinant এর তো কোনো দরকার নাই because you don't have any sort of vectors. This is just a simple wedge product. Like, since x square itself is a, it's not a form, it's acting like a scalar over here, so it will just go in front, and you have this dx1 wedged with dx2 wedged with dx5, something like this. Okay, this is how you generally do wedge product. But if I ask you, okay, take these wedges or take this volume form, and then I give you some vectors, I want you to find the consequence of these forms acting on those vectors, only then you would go for this determinant definition. Is that understood?
Yes, sir.
Okay. Now let's see an example, pretty simple example. Let's say v is equals to, again, this is an example from book on page 75. What they did here is that they want to find the following. dx1 wedged with dx2, but they're acting on these vectors, this v and w. What is this? Well, let's write it down first. dx1 wedged with dx2, and they will act on the vectors, the column vectors, so to say, 1 2 3 and 4 5 6. Now notice that you have two form, but the vectors have three components, but that really doesn't matter. How you do it? Well, take this guy, and just like inner products, it will just work with the components of x1, because if you write a vector like this, then this is the component of x1, this would go with the x2, and if there were a x3 like this, if there were the x3, then this would be your component for x3, right? So I think Nian asked that, okay, if you can have volume 3 form in a 4-dimensional space. I think this should answer your question. Like, these vectors, they're 3-dimensional, but the quantity you want to compute is a volume 2 form, right? So you can do that. So you would write it as, you want to be, rigorous and all that, you want to be extra careful, you can write it as this v1, or so to say v dx1 w dx2v dx2w, and this is just, this is acting at 1 and 4, right? because this vector is a column vector and you are just taking an inner product, something you are familiar from how to compute things that come with differential one forms. So we use that idea. We use the definition of our mapping of differential two forms, and we just put them together. So this will give you just 1. This guy will give you 4. This will give you 2. And this one, dx2w, will give you 5. And this is a determinant. And this is just what? 5 minus 4 times 2, 8. That is minus 3. So this is how you compute things. Okay. What does this mean? Well, it will become more clear when you see your change of variables, and you see that this is actually a Jacobian. Minus sign tells you about the orientation. 3 is a scale factor, but maybe we'll get back to that later. But for now, this is how you compute these things. And if you have, let's say, differential n forms like this one, dx1 wedged with dx2 wedged with dot 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 dx of n, and they are acting on some vectors v1, v2, v3 dot 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 dot, dot p of n, then this is just like this definition, this 2 by 2 definition. You would have a dx2 v sorry, dx1 v2 dx1 v of n. This will be dx2 v2, sorry, v1, not v2. I always mess up the indices. And so on. This would be an n by n cross n matrix. And there might even be cases where you are trying to compute an wedge product like this, but now the dimensions of the vector are less than the number of differential forms that you have. We'll also see how to deal with those cases as well, but that's not for today. So up to this point, do you have any questions? For now, at least get comfortable with computing these determinants. There are plenty of examples in the book. Look them up. If you don't understand, ask me in Slack. Okay. Any questions, anyone? No? Hello? Okay, if you guys don't have any sort of questions, I think I can finish with some algebraic properties of wedge products. I showed them on lectures. Try to prove them. This is the last thing for today, algebraic properties. Let's say you have omega and etas. I'm using the notation from the books again. And omega is a k form. We often denote forms with this big lambda that looks like a wedge. And the power over here will denote what form is it. So let's say this is a k form, and let's say this eta, this is a L form. Then the following properties hold. A multiplied with omega wedged with eta, where A is a scalar or a real number, whatever you want to say it. This is the similar thing or the same thing as this. This is one property. Second property is if you have omega 1 and omega 2, which are also k forms, and you want to wedge them with the eta, it will be just omega 1 wedged with eta, omega 2 wedged with eta. 3 is similar, and number 4 is perhaps the most interesting property. Not the most important, but it's pretty interesting. The proof itself is pretty interesting. It doesn't take much. It's just a few words, some logical words. You need to think logically to prove this thing. What I want you to do is that first of all, get comfortable with the computations of those determinants, how you deal with those 2 forms or 3 forms. Then try to prove these algebraic properties of these wedge products. If you cannot, then that's fine. But I would encourage you to do it, especially the last one. It's pretty interesting. And all it takes is some logical arguments, nothing else. All you need to do is to use this definition that omega is a K form, eta is a L form, and you need to keep in mind that wedge products are antisymmetric products. Then by some logical arguments, you would eventually end up with this thing. You don't even need to compute anything at all. So I think this is good for today, and maybe we can carry our discussion from this point, let's say next Friday or Saturday. So if you have any questions, I think you can ask right now. Any questions? Anyone?
No, sir.
Okay, so if no one has to share anything or no one has any questions, then I think we can conclude today's meeting, and I will give this recording in Vuex as well. So thank you. Okay, if you don't have any concern, do you have any concern or any type of thing that you want to share? If you want to, you can do that. I'm stopping the recording.